Hello, my name is Adriaan Knox. I'm from Hartnell, California. And what I'll be presenting to you today is a couple things. We're doing a project where we are doing outreach to high school students, and we are having them build some technology to incorporate their participation in the science that we're already doing. Also, we're characterizing a new type of very sensitive light detector. It's called a multi-pixel photon counter. So let me start with showing you about cosmic rays. We use cosmic rays to characterize these very sensitive light detectors because we know a lot about cosmic rays already. They're higher energy protons, mostly coming from outer space. They hit molecules in our atmosphere and they break apart into their constituents. On the ground, we see the muons, and the equipment that we use can be seen in this diagram. So first we have a high energy particle coming in from outer space, the yellow proton. Hits a particle in our atmosphere, eventually breaks up into various constituents, one of which is a muon, which makes it to the surface of the Earth with still some high energy. We use a plastic scintillator, which is plastic impregnated with special chemical, which also has a lot of stopping power. So actually, every minute, hundreds of muons are actually traveling through your body, but your body doesn't have a lot of stopping power. The scintillator is engineered to stop the muon. When the muon strikes this special plastic, a photon is emitted, and the photon travels through the scintillator to our detector. Now, this where the MPPC is here, usually since 1939, even before that, they were using PMTs, which are photomultiplier tubes, which cost 20 times as much. They're fragile. We went to a conference in San Francisco last week, and somebody came up to our poster and said, my students are always breaking these photomultiplier tubes, and they're very expensive. So what we're doing is looking for an alternative, a viable alternative to that, 7-year-old technology. So after our MPPC, we get an electron and we can get data. So this is what the scintillator looks like. It looks like a clear plastic, and that's what the muons strike, releasing a photon, which goes into optical fiber. It's hard to see there, but the optical fiber is actually impregnated, embedded into the scintillating plastic, which directs the photon to the detector there in the blue box on the right. So this presentation is partly to be a sort of tutorial for the high school students that I said we would be working with, so they can have some steps to build the detectors that we build. So this is a picture of a photomultiplier tube. This is the outgoing technology that we're interested in replacing. Now, this is what we're interested in replacing it with. There's MPPCs and there's also SIPMs. They are very, very small. This is a 3 by 3 millimeter square. That's the one that we were investigating. You can see them up there on the top. That's a picture of them. What we're going to be having is them soldering. So there's a picture of one beginning to be soldered. And it's a delicate process. There's plastic there, so that's something to consider. It doesn't just come out of the box like a photomultiplier tube does. There is some assembly involved. These are the circuits that we build and what we're going to be having them build. There they are finished. There's a power supply there with this red wire coming off of it. It's high voltage power supply. The other circuit was the detector circuit. Some drilling involved. You got to make sure that everything fits in your boxes properly. Some soldering, of course. There it is all together. You can see the NPPC is actually there's a hole drilled in the casing for the NPPC, so it's easier for us to direct the optical fiber to the detector. Oh, detectors. So there's a hole, there's the picture of the hole, and it's very hard to do that part. So we're gonna have to try to work something for the students, because even for me, I have some fabrication experience, and that part was actually difficult. It's very hard to get that lined up. You gotta come back with a needle file and open it up a little bit, and it's just, could be better. So we construct the circuits, and we test them by using power supply. You can see my arm up there, goes to the power supply. Hit the switch, we put 10 volts in, and we get negative 30 out. That's what the solid state detectors, the MPPC and the SIPRIM use. Also now you can see that I've taped up the detector with black tape, so that way we don't destroy the detector. These can still be destroyed. They cost, 1/20th of a PMT, so that's why now we can have high school students being incorporated into the science very early. And in my community, that's pretty rare opportunity for somebody to be brought into the fold. So what I do is I take that off on the end, so that way we're not actually having photons hit the detector. We want to protect the detector. There's no light sensing going on. What you see on the oscilloscope there, like I said, the 30 volts, you can see on the fluke meter there, there's 30 volts, negative 30 volts powering the detector. What you see on the scope is actually noise. So they're very noisy. They're cheap, but they're noisy. So that introduces problems in and of itself. So this step right here is to make sure that your detector even works. You need something. It needs to be some type of activity to show you that it's alive. So that's how we verify that. Now, to get over that noise, previously we ran 2 in coincidence. Now we have moved to running 4 in coincidence. Eventually we would like to put them in an array. So there'd be a square with 1 on each corner, and that's the next step. We need to find out how much delay the wires introduce into the process, and so we're continuing from here. But this is the setup that you'll see the data from later on in the presentation. Here's a closer look of the scintillating plastic. You can see it on the side view there. It's glowing kind of an interesting color. It's kind of nice color. And you can see that the optical fiber is actually, there's a groove milled into this plastic, and the optical fiber is embedded. The greasy stuff is actually dielectric grease, which the manufacturer of the scintillating plastic told us to use as optical coupling compound, which I wouldn't have thought that it could do that. So that's a clear gel that actually allows the photons, it'll pass the photons. If there's any gap between the optical fiber and the scintillating plastic, the grease will transmit the photon through it. Through total internal reflection, the photon is directed through the fiber towards the detector. Here's a larger look at our entire setup with all of the equipment. You can see we have some NIM-bin modules down here, and those are our light type boxes there. There's 4 detectors all together there in this box with the red tape on it. So the first step after ensuring that you actually have some activity from these detectors that you built is to look at them on the oscilloscope when they're unwrapped, all fully assembled, and this is actually a strike of a muon hitting each detector and releasing a photon. That's exactly what we want to see. You can see that they're coming in at, right at the same time. You can see, and they're falling off right at the same time. So that's beautiful. That's exactly what we want to see. Here it is on a screen capture from the oscilloscope. This is what we want to see. Now, you watch the oscilloscope long enough, and you're going to see some stuff that you don't want to, because this is experimental setup, and it kind of has a personality of its own. Sometimes, it has quirks and stuff, and you find out a lot about your equipment, and so that's another challenge that you're going to be presented to the high school students. You can see on the top 2, channel 1 and 2, the yellow and the blue, there is no wave. There's no signal. Yet we still had our oscilloscope triggered. which is bad. That's very bad. This is not what we want. We want quadruple coincidence. So it's very perplexing to us. Why is the oscilloscope being triggered as if all 4 detectors had waves, had a strike upon them, yet we're only seeing 2 on the scope? So that was a problem, and we were very perplexed about that. That shouldn't happen. You know, we were using NIMBIN modules to make sure that we get the signal after it's met certain parameters, which is actually quadruple coincidence. So seeing this on the scope is completely counterproductive. You have to go back to square one. So now we look at each signal and the signal coming out of the discriminator and making sure that we get a logic pulse from each signal. If you have a good enough oscilloscope, you can do that for multiple channels. Here's 2 channels at a time. Another problem that we had was that the logic signals are actually sometimes missing from 2 channels. There's our problem. No wonder we're only seeing 2 on the scope. Some of the logic signals aren't coming through. Apparently, the logic gate is seeing the logic pulse, yet we're not seeing it on the scope. So somewhere there's a breakdown in communication. This is a quirk of this particular NIMBIN module, this logic unit, where it has a veto plug, and we were not utilizing that plug, yet it was affecting the operation of our setup. So we decided not to use that channel, and lo and behold, all of our signals came back. Here's another problem. The logic signals that we got sometimes were not beautiful like these ones down here. They were just erratic, all different lengths, and that's hard to explain. So through some adjustments of the discriminator, we were able to dial that in. This one right here is the one where, you're just, this is the most frustrating one because this is actually inherent in the building that we're working in. Our detectors are so sensitive that it's going to pick up a student in the other room hitting a light switch. We were in a very old building, and this is what we get on our scope. So we can't really do a lot to negate this at this point. So what we're going to use later is a data acquisition through a PC to just get rid of these data sets. So this right here is where you really want to pull your hair out, but you got to resist that urge because that's a part of the process. Although I would probably let her pull on my hair if she wanted to. So now, what we do, like I said, we hook up to the computer. This is a DAC right here, and that's actually digitizing our waves that would be going into the oscilloscope. We're now sending them into the computer.
So you're a minute 40 past the total. Yes.
Okay. So here we are on the oscilloscope with the same thing that's on the computer with the same thing that was on the oscilloscope. Here's the data coming in. Here's the same thing that we saw on the oscilloscope, except it's on the computer now. Here is 2,000 of those data sets plotted. We get a nice pattern of lining up where they're coming in at the same time. Channel 4 is special because it's on top. Here is each channel compared to channel 4. And also here's time versus time. They should be linear, which you see on the right there, which is showing that we have coincidence. They're all coming in at the same time. If you'd like to see a video of our setup and our experiment, there's a link. And thank you for your time.
Okay, so we have no time for questions unless